Welcome to Unit 8B skill video for skill number 80. I can simplify, evaluate, and rewrite radical expressions by using rational exponents. We'll begin our notes on page 80A, radical expressions and rational exponents. We'll start by talking about radical expressions, and what we have is an expression that uses a radical. For example, you might have the square root of 9 or the square root of 625. Those are radical expressions. It is possible to change the index. So we could say the fourth root of 625, or maybe we have the third root of 64. The number that is indicated inside the root is called the index, and if 1 is not written, we assume that index to be a 2, so the square root. And we're most familiar with the square root because we've been seeing this one all year long. Something to notice about the indexes are if you have an odd index, like this, you have only one real root, only one real answer. And in this case, the answer is 4 because 4 to the third is equal to 64. If you have an even index and a positive radicand, like we have here, you get two real roots. You have the plus and minus 3 in this case. Or since we have the fourth root of 625, this is plus and minus 5, because 5 times 5 times 5 times 5 is equal to 625. And there's 4 of those, which matches our fourth root. You can also have the even index with a negative radicand. So if you did the square root, and I'll draw the 2 in there, the square root of negative 16, because it is a negative radicand, this is called the radicand, we get no real roots. And for those that are remembering back to how to solve this, the answer is 4i, or plus and minus 4i. So there's our imaginary roots. But we're just focusing on real roots for this lesson. And finally, regardless of the index, whatever number it is, whether it's a 5, 2, 10, x, whatever it is, if your radicand is 0, then you have only one real root, and it is, in fact, 0. In example 1 below, I've shown how it's written out in words. The fourth root of 625 can be rewritten as 4 root 625, like I did up here. You could also, if you wanted to, write it as rational exponents. So the root, the index of the root, can be written as a denominator. So what we have is 625 to the 1/4, and the value of that is 5, or more technically, the full answer would be plus and minus 5. If you wanted the fifth root of negative 32, you get the answer of negative 2. Notice it is a odd index, so we only have one real root. Or the third root of 8, that is also an odd index, so we only have one real root, and that's 2. Properties of radical expressions are very similar or identical to the properties that we knew about square roots. For example, if I wanted to know the value of the square root of 2 times the square root of 8, I could rewrite that as the square root of 2 times 8, which is root 16, which we knew to be plus and minus 4. Similarly, the division, we could say what is root 75 divided by root 3, and that is equal to root 75 over 3, or root 25, which is equal to plus and minus 5. So those properties that we learned with square roots are identical here with radical properties. So if I were evaluating these, the same value would be true if it was the fifth root of root 2 times the fifth root of 8. We could put a 5 there and a 5 there, and then this value would change to whatever that value is. Some number greater than 1 and less than 2. Example 2 actually demonstrates on how to simplify expressions like this. Now this one, it actually turns out is in simplest form. So let's take a look at the process so that we can apply it to problems that can be simplified. What I have here is the fourth root of 1250 x to the fifth y to the fourth z. If I want to simplify these expressions, the first step I need to take is to expand them. So I wrote the prime factorization of 1250, and if I wanted to, I could say, alright, this is 25 times 50, which is 5 times 5, 5 times 10, 5 times 2. So the prime factorization is 5552. I'll write that there. I can expand the x's, x to the fifth, I write 5 of them, y to the fourth, I write 4 of them, and then z, there's only 1 of them, so I write it once. You'll find that eventually we won't need to write out the expansion of the variables. I'll show you a shorter way to do it. But the expansion of the numbers is really useful. So in step 2, we find groups which match the index size. And since our index is 4, we're looking for groups of 4. So we have 4 5s, which I've called out right here. And we have 4 x's, and we have 4 y's. And all of those groups get pulled out to the front. So you're actually taking the fourth root of that. So the fourth root of 5 to the fourth is going to be 5. The fourth root of x to the fourth is x. And the fourth root of y to the fourth is y. And we're left with a 2 inside, an x inside, and a z inside. So we can't simplify that down any further. You'll see in the next example I did the same process. The only difference is I didn't write out all of the letters, all of the variables. For x to the fifth, I broke it into the group of x to the third times x squared, because that matches my index. Y to the ninth, I broke into y to the third, y to the third, y to the third, because it matches my index. And then z to the fourth, I did a z to the third times z to the 1. And then I started pulling out my groups. Pull out a group of 3 2's. Can't do anything with the 3 or the 5. Pull out one group of x to the third, which is equal to x once we take the third root of it. And then I have 3 groups of y to the third, so I'm able to pull out 3 y's. And in the end, I have the z to the third, and I'm able to pull out the z to the third. This leaves me with 3 times 5 times x squared times z on the inside. So 2x y to the third, z, and then we have the third root of the pieces that are left. This can be extended when we multiply 2 radicals with a common index, and we have the fifth root on this radical and the fifth root on this radical, so we can combine them and we get 8 times 16, x to the fourth, x to the third, and y squared. And if we were to simplify that out, 8 times 16 is 128. The x's combine to be x to the seventh and then y squared. So I expanded it, I combined them, and then I've expanded it and pulled out my groups. So a group of 5 2's can come out, and we're left with 2 squared on the inside. a group of 5 x's can come out, and we're left with 2 left over, and then the y squared, there is no group large enough to be pulled out. The final part of the skill is being able to convert between a rational exponent and the radical form. So we're used to seeing it like this. We should be able to rewrite it as a fraction. For example, if I had the 5th root of 7 squared, I could write this as 7 to the 2/5. So the numerator, do it in a different color. The numerator matches the power on the inside, and the denominator matches the power of the index. We saw that earlier when I said 64th to the 1/4 was the same thing as the 4th root of 64. Alright, so here's a few examples. Under example 3, what we have is the 3rd root of 5, and that's raised to the 6th power. So I write 5 to the 1/3, and I take that value and raise it to the 6th power, which I can rewrite in the exponential form by combining my two exponents to be 6/3, and then I reduce 6/3 and I get 5 squared and a value of 25. Ultimately, we want to be able to move fluidly back and forth between the two forms, because sometimes one form is more beneficial than the other. For example, evaluating 8 to the 2/3 is difficult, so if we rewrite it in exponential form, in radical form, we have the 3rd root of 8 squared. We take the 8 squared and make it a 64, and we know the 3rd root of 64 is 4. So in the first example, it was difficult to evaluate in radical form, and in the second, it was difficult to evaluate as a rational exponent. Third one, we also go rational exponent to the radical form, and then simplify the radical form. And in the fourth example, we start in the radical form, switch it to the rational exponent, so 3/6. Reduce the 3/6 and then convert it back to a radical form to find the value of 8, or more accurately, plus and minus 8. Alright, the meat of the lesson rests in our ability to take a number that is in a rational exponent form and convert it into a number that is in radical form, or perhaps going backwards where we have something in radical form and being able to move it into a rational exponent form. We should also be able to reduce equations, radical equation or expressions like this. Being able to move between these two things fluidly is going to prove very beneficial to us, and understanding the underlying principles at work here will also help us in the latter part of this unit. Thank you.